All right, it's time for discussion 6.2, reaction order and mechanisms. All right, so before we begin, I want to start with a little warm-up question to review things we talked about in 6.1. All right, so this question says, excess magnesium was added to a beaker of aqueous hydrochloric acid out of balance. A graph of the mass of the beaker and contents was plotted against time, which is line 1. So we'll learn in Unit 8 that when you mix a metal like magnesium with an acid, you'll produce hydrogen gas. The hydrogen gas will escape the beaker, and so you'll see the mass decrease. So the question wants to know what change in the experiment will give us line 2. So before we look at the choices, let's evaluate the two lines. Now if we look at line 2 versus line 1, we see that line 2 begins with a steeper slope. That means that more mass is being lost per unit time in line 2, which means line 2 is being produced at a faster rate. We also see that line 2 loses more mass in total than line 1. We all know stoichiometry. If line 2 loses more mass, then more hydrogen is produced. If more hydrogen is produced, that means we're starting with more reactant. It's like making brownies. If we want to double the amount of brownies we're going to make, we're going to have to double the amount of mix we're going to use. So let's now look at the choices. Number 1 says the same mass of magnesium, but in smaller pieces. Well, using smaller pieces would give us a faster rate, but if we're using the same mass, then we'll produce the same amount of product that we produce in line 1. So it's not going to be choice 1. Choice 2 says the same volume of a more concentrated solution of hydrochloric acid. Well, we remember from Unit 1 that if we multiply the volume of an acid times its concentration, we'll get the number of moles of solute. So keeping the volume the same and increasing the concentration will give us more moles of hydrochloric acid. So that would give us the amount of product in line 2, and increasing the concentration will also increase the rate, so that would give us the increased rate. So it's looking like number 2 is a good choice. Number 3 is a lower temperature. We know that's not true because lowering the temperature would lower the rate. So the answer to this question is B, 2 only. All right, so rate laws. A rate law is an equation that will link the reaction rate with the concentration of reactants in a reaction. And the general form of a rate law is rate equals K times A in brackets raised to the X power times B in brackets raised to the Y. And we'll talk about what all those factors mean in the next slide. So the order of a reaction is a measure of how changes in each reactant will affect the rate of that reaction. So diving deeper into the rate law, K in the rate law is known as the rate constant. And the rate constant will be different for each particular reaction. X and Y are the orders with respect to reactants A and B. Now, A in brackets and B in brackets, if you remember from Unit 1, anything put in brackets is the concentration of that thing in the brackets. So A and B in brackets are the concentrations of reactants A and B. And the sum of X and Y will give you the overall order of a reaction. Now the rate constant can change, and it can only change based on one thing, and that one thing is temperature. Now molecularity just refers to the number of reactants that are involved in the rate law. If a reaction is unimolecular, there will only be one reactant in the rate law. If it's bimolecular, there'd be 2. If it's trimolecular, there'd be 3, etc. So we can experimentally determine the rate law in 2 ways, using the initial rate method or a variety of graphical methods. So let's look at initial rate method first. The initial rate method is best for relatively slow reactions. Now to do this, we want to measure the initial rates of reactants at various concentrations. And we want to see how changing the concentration of one reactant will affect the rate. Now if we want to see how changing one reactant will affect the rate and not the other, then we're going to have to look for data where one of the reactants' concentration is remaining constant and the other one is changing. And think about it. If we want to determine how changing the concentration of one reactant only affects the rate, then we'd have to keep the other one constant. Because if we're changing the concentration of both of them, there's no way for us to know which one is affecting the rate. So to determine the order with respect to ammonium, I'll use experiments 1 and 2. I see in experiments 1 and 2 that the concentration of the nitrite ion remains constant. And in reactions 1 and 2, we see the concentration of ammonium doubling. And as the concentration of ammonium doubles, we see that the rate doubles. So the order with respect to ammonium would be first order. Now let's do the same for the nitrite ion. So for the nitrite ion, I want to find two experiments where the concentration of ammonium is remaining constant. So I'll use experiments 5 and 6. So we see that in experiments 5 and 6, the concentration of nitrite doubles. And we see that the rate also doubles. So the order with respect to the nitrite ion will also be first order. So to do this, we're going to find two trials where the reactant we're interested in changes, and it's easy if we see the reactant doubling, and the other reactant remains the same. We'll see what happens to the rate when the concentration of the reactant changes. So if the reactant doubles and the rate doubles, it'll be first order, and the rate law would look like this, where rate would equal K times the concentration of our reactant raised to the first power. If the the concentration of the reactant doubles and the rate quadruples, then it'll be second order, and it would look like this. All right, so why does this work? Well, it's just math. If something is second order, then essentially we'd be squaring that concentration to find the rate. So in this example, if the concentration of A is 1 and the rate is 1, we could take the concentration of A and double it, and the rate would go up to 4. Because basically what we're doing is squaring the concentration. So 1 squared equals 1, and 2 squared equals 4. So doubling the concentration quadruples the rate. This question says, what would the order be with respect to reactant A if doubling A did not change the rate at all? So take a moment, pause the video, and try to work out what order that would be. All right, so first here we have the concentration of A being 1 and the rate being 1. Now, if doubling the concentration doesn't change the rate, then making A 2, the rate would still be 1. So we know that raising anything to the 0 power will give you an answer of 1. So if doubling the concentration of a reactant does not change the rate at all, then it would be 0 order. All right, so take a moment and practice with this problem. It says the following data was collected for the reaction of nitrogen monoxide and oxygen gas. Deduce the order of this reaction with respect to A and B, write an expression for the rate law in this reaction, and calculate the value of the rate constant. So it wants 3 things. So take a moment, use the steps on the previous slide, and see if you can come up with those 3 things. All right, so the first thing I'll do is try to determine the order with respect to NO. So I'm going to want to find some data where the concentration of oxygen remains constant. So I'll use rows 2 and 3. So I see in rows 2 and 3 that when I double the concentration of NO, the rate quadruples. That means that the order with respect to NO is second order. Now I'll do the same for oxygen. So to determine the order with respect to oxygen, I'll look where NO remains constant. And I see that doubling the rate doubles the reaction. So the order with respect to oxygen would be first order. And the rate law then would be rate equals K times the concentration of NO squared times the concentration of oxygen raised to the first power. Now it wants us to calculate K. So I'll rearrange the expression to solve for K and plug in the numbers. And when I do that, I get 0.020 decimeters to the 6th times moles to the -2 times seconds to the -1. Now don't worry right now about the units of rate constant. In class, we will go over how to derive those units. It's actually not as hard as you think. You can actually try it right now. If you want, look at the units of each factor in the table and plug them into the equation without the numbers and cancel out everything and see what you get. All right, so reaction mechanisms. Now, reactions, we know, are not usually as simple as they're written, and they'll occur in multiple steps. What we see usually is the overall reaction, which is the sum of all the steps. Now, so here we have an example mechanism with 3 steps. And just like what we did when we worked with Hess's law, we can cancel out reactants and products if they're on opposite sides of the arrow. So I look here and I see that I have X2Y4 on both sides of the arrow, so we can cancel those out. I also have 1 mole of X2 on both sides, so I can cancel those out. On the reactant side, I have 1 mole of Y and 2 moles of Y on the right. And so the 1 mole of Y on the left will cancel, and 1 of the 2 on the right will cancel. Doesn't look like there's anything else we can cancel here, so the overall reaction will be 2XY2, making 2XY plus Y2. Now, intermediates are species that are produced in one step of the reaction, but are consumed in another. So they'll cancel out and won't appear in the overall reaction. So in this case, our intermediates are X2Y4 and X2. Now, what would a catalyst look like? Now, a catalyst is something that we add to a reaction whose only function is to lower the activation energy and produce a faster rate. The catalyst itself is not changed during the reaction. So it'll cancel out because it'll be on both sides of the equation, but it's a little bit different than an intermediate, because instead of being produced in one step, it'll actually be something that we add. So we'll see it as a reactant, and we'll also see it spit out as a product. All right, so why is reaction order the way it is? Well, it's based on something called the rate determining step. The rate determining step is the slow step in a reaction mechanism, and it will always be the step that determines the rate because it has the highest activation energy. I like to think of the rate determining step being like me driving down Reston Parkway when I'm on my way home from work. Now, I like to drive a little bit fast. Not so fast that I get a ticket, but faster than most. Now for me, the slow car in front of me is the rate determining car. I can only drive as fast as the car in front of me, and I can't speed up until that car goes away. All right, so it's the same thing with a reaction. And if you look at the rate determining step in a mechanism, the coefficients of the reactants will be the order of that reactant. So if a reactant isn't in the rate determining step, then it doesn't affect the rate and it'll be 0 order. So here's an example. Reaction of 2 moles of nitrogen dioxide gas reacting with fluorine gas to produce 2 moles of NO2F gas. So we have 2 steps in the mechanism. We see that the first step is the slow step, and in that step we have 1 mole of nitrogen dioxide and 1 mole of fluorine. Now if we look at the overall, we see 2 moles of nitrogen dioxide, but in the rate determining step only 1 of those 2 moles is participating in the step. So when we do the rate expression for this reaction, we'll have fluorine to the first order because there's 1 mole of it, and nitrogen dioxide to the first order because there's 1 mole of that. So the rate law will be K times NO2 times F2. All right, so intermediates and rate laws. So only reactants that you see in the overall reaction will show up in the rate law. So when we have an intermediate in the rate determining step, usually it will not appear in the rate law, but sometimes it will. And we'll look at this example to illustrate that. Now we see in the rate determining step, well actually let's go ahead and determine the overall reaction so we can see what should appear in the rate law. So we have 1 mole of N2O4 on both sides of the equation, and it doesn't look like I can cancel anything else out, so the overall reaction will be this. So we have NO2 and carbon monoxide in the overall reaction. So we cannot have any other reactant in the rate determining step. But in this particular reaction, if you look at the fast step, you see that that reaction up top has a double arrow. That means it's a reversible reaction. Now we'll talk a lot more about reversible reactions in topic 6.3, which is equilibrium. But if you remember from Chem 1, Le Chatelier's principle says that if we add more nitrogen dioxide, we'll increase the concentration of N2O4. Now N2O4 is an intermediate that is involved in the slow rate determining step. Now since changing the concentration of NO2 will change the concentration of N2O4, the concentrations of NO2 will have an indirect effect on the rate of that reaction. So they're not appearing in the rate determining step, but they're affecting the rate determining step, and so they will appear in the rate law. So the rate law for this particular reaction would be rate equals K times NO2 to the second order times carbon monoxide to the second order. All right, so here's a practice question. It says consider the following reaction, and there it is. It says the temperature is less than 227 Celsius. The rate expression is K times NO2 to the second order. Which of the following mechanisms is consistent with this rate expression? So take a moment, pause the video, and see if you can find the correct choice. All right, so we see in the rate constant that the NO2 is to the second order. That means in our rate determining step, we should have 2 moles of NO2. All right, so let's look at choice A. In choice A, we have the same exact reaction we had on the previous slide. So there are indeed 2 moles of NO2 that are having an effect on that rate determining step. But there's also 2 moles of carbon monoxide in that rate determining step. So choice A can't be true because carbon monoxide doesn't show up in our rate law. The same thing applies to choice B, so we know that is not true. In choice C, we have only NO2 in the rate determining step, but there's only 1 mole of it, so that is not consistent with that rate law. And choice D has only 2 moles of NO2 in the rate determining step, and so choice D is consistent with our rate law. Here's another one. Considering the following reaction. Blah. The rate expression for the reaction is found to be rate equals K times bromide times bromate times hydrogen ion to the second order. So which statement is correct? Take a moment, pause the video, and see if you can work this one out. Okay, so choice A, let's evaluate each of the choices. Choice A says the overall order is 12. Well, if you recall from the beginning of the discussion, the overall order of the reaction is the sum of all the individual orders of each reactant. So the overall order for this reaction will be 1 plus 2, which is 4, so choice A is out. Choice B says doubling the concentration of all the reactants at the same time would increase the rate of the reaction by a factor of 16. Now that actually sounds correct. If a second order reaction would quadruple the rate, then I would expect a fourth order reaction to increase the rate by a factor of 16. But before we select that, let's evaluate the other 2 choices just in case. Choice C says the units of the rate constant are moles per liter per second. Well, again, we'll talk more about how to derive those units in class, but moles per liter per second is actually the unit for a first order reaction, so that is not correct. Finally, choice D says a change in concentration of bromide or bromate does not affect the rate of the reaction. Well, that is not true because both of those species are in the rate law. So indeed, the answer is choice B. All right, we can also determine rate from a graph. And there's 2 main types of the rate that we're interested in, instantaneous and initial. So instantaneous rate is just the rate at any given moment in time. And initial rate, is, I had a big dinner. Initial rate is the rate that we get the moment the reactants are mixed. Now it's important to note that the initial rate will always be the fastest for any reaction because the moment you mix the reactants, you have the greatest number of reactants colliding. So if we draw a tangent line to the very first measured rate point, so we basically continue that line as if it would be linear, we can measure the rate of the initial reaction. Now the slope of the line will give us the rate of that reaction, and the units will be cubic centimeters over seconds. Because when we look at a graph, we know that the y-axis is always divided by the x-axis, so the unit of y is cubic centimeters, and the unit of x is seconds. And if we wanted to solve the rate, all we have to do is get the slope of that tangent. So the slope of that tangent is 2.5, and the unit is cubic centimeters per second. So 2.5 cubic centimeters per second is the initial rate of that reaction. Now for the instantaneous rate, we would draw a tangent line to any point on the curve. Now the slope of that tangent line will give us the rate at that moment in time. So this example is at 50 seconds. So again, the slope will give us the same units of cubic centimeters per second. If we solve for the slope here, we find that the rate is 0.33 cubic centimeters per second, which makes sense because that is slower than the initial rate. All right, they'll also could give you, mainly on paper 1, multiple choice, graphs of rate versus concentration or concentration versus time. Now to figure these out, to determine order from these graphs, you can actually use just your ability to analyze graphs to solve these problems. So if we look at a zero order, for zero order, we would expect changes in the concentration to have no effect on the rate. And that's exactly what we see. We see the rate remains constant as the concentration changes. For a first order, we know that doubling the concentration will double the rate. That is a direct relationship. So for a first order graph, we'll see a graph for a direct relationship, y equals x. For second order, we know that we are quadrupling the rate every time we square the reaction, so we'll see an exponential growth curve. Now for concentration versus time, it's a little less obvious. Basically, these are just rate curves. Now we see for zero order that the concentration will decrease at a constant rate and will not change as the concentration changes. Now for first order, we know that the concentration, because excuse me, because for first order, as we double the concentration, we double the rate. As we half the concentration, we half the rate. So that is an inverse reaction, is an inverse relationship, so we'll see an inverse curve. And for second order, because it's a squared relationship, we'll see an exponential decay curve. All right, finally, the Arrhenius equation. So Svante Arrhenius of Arrhenius acid-base fame developed a relationship between the rate constant and activation energy. And the equation is K equals A times the inverse natural logarithm of negative EA activation energy over R times T. Now this equation is in the data booklet, but you can ask Dr. Textall, but I have not seen any examples where they have you calculate any of these factors, because it's very rare for the IB to give you plug and chug kind of equations. Now in this equation, A is the frequency factor, which is a number that represents the likelihood that collisions will occur with the proper orientation. E sub A is the activation energy, T is the temperature in Kelvin, and R is the universal thermodynamics or gas constant. And it has a value of 8.314 joules per mole Kelvin, or 8.314 times 10 to the negative third kilojoules per mole Kelvin. And that value is in table 1 of the data booklet. Now if you take the natural log of both sides of this equation, it becomes the natural log of K equals negative E sub A over RT plus the natural log of A. Now the form of this equation should look very familiar to you because this is just the equation for a straight line. So when K is determined experimentally at several different temperatures, activation energy can be calculated from the slope of a plot of natural log of K versus 1 over T. So we're going to use Y equals mx plus b. So we see that in this particular equation, y is the natural log of k, and we see that that is the y-axis. We see that x is 1 over t. Now this term is the slope times x, so if x is 1 over t, that means that the slope becomes negative activation energy over r. So we can use this relationship to calculate the activation energy because the slope can be calculated and r is a constant. So here's an example of doing this. It says the conversion of CH3NC, I believe it's called methane nitrile, or methane, I'm going to stop, CH3NC into CH3CN. Alright, so that's an exothermic reaction, which can be represented by the following equation. So the reaction was carried out at different temperatures, and a value of the rate constant K was obtained for each temperature. A graph of natural log of K against 1 over T is shown below. Calculate the activation energy for the reaction using table 1 of the data booklet. So I want you guys to try this one on your own. All you have to do is calculate the slope and set it equal to the negative activation energy over R and solve for activation energy. So pause the video, take a moment, and give that a shot. Okay, so we know that the slope is equal to the negative activation energy divided by R. So we can rearrange this equation to solve for activation energy, which we see is equal to negative R times the slope. So all we have to do is calculate the slope. When I do this, I like to find a point where the line intersects a line on the graph, because it at least makes you easy to determine your change in x. So we plug in the numbers to find the slope. I get the slope to be negative 19,600. Now that we know the slope, we can plug it into the equation, multiply it by R, and that gives us a value of 163,000 joules per mole. Now I got joules per mole here because I plugged in 8.314. If I want my answer to be in kilojoules per mole, I can either plug in 8.314 times 10 to the negative third, or just divide the answer that I get by 1,000 to get 163 kilojoules per mole. And you want to be really careful when you're looking at the unit of x here as inverse Kelvin. Sometimes you might see it as times 10 to the negative third inverse Kelvin. Now, when you're doing that, you have to make sure when you're calculating your slope that you plug in times 10 to the negative third. Think about a graph where the unit of an axis is millions of people, and the numbers you see are 1, 2, 3, 4, and 5. Well, each number means millions of people. So 1 million, 2 million, 3 million, 4 million. If the unit of the x-axis is something like times 10 to the negative third, and the numbers are 1, 2, 3, 4, 5, you have to make sure that the temperatures you input are 1 times 10 to the negative third, 2 times 10 to the negative third, etc., etc. And you'll actually see that used in the homework assignment for this particular discussion. So that is all. That is the HL extension for for Unit 6. And it seems a little difficult. This is the longest video I've made so far. But if you practice everything, you're going to do just fine on this. Thank you for watching. Please bring any questions you have to class. I'll be happy to answer them. And like I said, we'll definitely be working on deriving the units of K for you. Okay, have a great one.